For this project, we are to use spectroscopy. Spectroscopy is a method in optics in which white light emission, specifically for us an LED light, is seen through a spectrometer, and the result seen are several lines of the color spectrum that the white light is composed of, and this is captured through the spectrometer and pictures are taken with an iPhone to upload these images to a spectral workbench site in which graphs are created and the images are analyzed. The purpose of this lab is to use a constructive spectrometer to exhibit light interactions through a liquid, relating it to Beer's law. Beer's law states that the absorbance of light by a particular substance is determined by the concentration of that substance in a solution. It is given by the equation A equals sigma LC, where A is the absorbance, sigma is the attenuation coefficient, L is the path length through which the light passes through the solution, and C is the molar concentration of the substance. In our case, the path length would be the width of the cuvette. Optics. For this project, we want to measure the concentration of chlorine specifically, which is colorless. And with chlorine being colorless, we can use a chemical reaction to alter the color of the solution in order to use our spectrometer properly and obtain proper spectra. The goal of our project is to be able to measure various chlorine concentrations in random water samples. Initial research of our project showed that chlorine has the ability to react with a chemical known as DPD and produce a red colored solution called Worcester dye. And measuring the absorbance of this red colored solution can allow us to determine the concentration of chlorine in the sample depending on the hue of red or pink that we get. The total cost of materials for the project include the DPD and potassium permanganate solution that I will speak about later, concludes to about $15. The foldable spectrometer from Public Lab costs about $6, and any supplies used to put together, such as tape, glue, does not cost anything, as we already had the supplies and the diffraction grating was given to us by Professor Zhao. Here we see the smartphone spectrometer construction. The spectrometer created is based on a cardboard spectrometer design found on Public Lab. The design is made of a cardboard foldable spectrometer, and the cardboard was folded along the lines shown in the proper orientation, and the diffraction grating given to us by Professor Zhao was taped to the end of the spectrometer using electrical tape, and the electrical tape helped block out any surrounding light and provide us with proper spectra, and the surrounding of the spectrometer itself was taped with electrical tape in order to prevent any light leakage. The spectrometer was then taped to the camera of an iPhone 5S to use as a final spectrometer and iPhone setup. Proper spectra are only achieved once we calibrate the smartphone spectrometer, and we use spectralworkbench.com to calculate our iPhone spectrometer. This website allows us to capture a spectra of our LED light source, our flashlight, and use these spectra to consistently measure the absorbance spectra from our data samples, the separate solutions we have of the DPD Worcester dye, and the captured calibration spectra is shown below when passing the LED light source to flashlight through the spectrometer itself. to create our specific samples, we went through serial dilutions. These dilutions were performed to obtain 4 samples with our initial molarity of 0.1, and then 3 others that came to 0.01 molar, 0.001 molar, and 0.0001 molar. Serial dilutions are performed by filling test tubes with, in our case, 9 milliliters of pure water. Then using a pipette, 1 milliliter of the 0.1 molar stock solution is added to the first test tube and mixed thoroughly. That creates a 1 to 10 dilution ratio. Then 1 milliliter of this 1 to 10 diluted ratio sample is placed in the next 9 mils of water to create a 1 to 100 ratio. And then 1 mil of this 1 to 100 ratio sample is placed in another 9 mils of water to create a 1 to 1000 ratio sample, thus increasing each ratio tenfold and giving us proper samples. The spectra shown are what we captured by passing light through the potassium permanganate solution itself first without adding the DPD. And they are shown from top to bottom in order from pure water, and then 0.0001 molar solution, and then third is a 0.001 molar solution, fourth is a 0.01 molar solution, and the last 3 include the spectra we captured for the 0.1 molar stock solution. We took these multiple times in order to allow the light to properly pass through because this was the darkest sample.